Hi everyone, welcome to the continuation of our kinematics video. So we have an original video. Please do watch that video. Hopefully you've watched that video, and now we're continuing with other sections. And then like the video, subscribe to our channel as well. We would appreciate it if you can just support the channel, and then also just click the notification bell so that whenever we upload a video, you can actually just know that we have uploaded a new video. Otherwise, guys, do enjoy and just make sure that you follow and leave a comment as well. All right, we're just going to talk about graphical presentation of motion. So particularly we're going to talk about three graphs. We're not gonna it's rare that they'll ask you about the other ones, so I'm just going to focus on three graphs, and then it's easy to extend it to any type of graph anyway. All right, so I'm going to focus on the position. So what I will be doing is I'll just be focusing when the position is on the x-axis, like a particle is here, after some time is here. So everything is going to be on the x-axis, right? So we'll be looking at things like position and displacement in the x-axis, right? On the x-axis, sorry. So that's what we're going to be looking at. So the graph that we'll be looking at is just going to be the position graph. It's x versus t. So this is known as the position time graph. Maybe I'll write that when I have a graph. And we're going to focus on v versus t. We're going to focus on a, which is acceleration, versus t as well. So all of them are going to be plotted with respect to time, and then we're just going to look at different situations and see how those situations are actually going to pan out in our case. All right. Okay. Now, all right. So before we start with any graphs, I'm just going to mention a few things, which is the slope and the area. I think that's going to be very important, and the types of graphs we can draw basically. So I'm going to focus on three graphs. So in mathematics, I think you should be familiar with a parabola, right? So this is a parabola that is actually on it's basically on the x-axis 0. So this is normally given by y is equals to x squared. So it's intersecting, or the turning point is at y is equals to 0. So that is what is happening. So this is the parabola. So the part that I'll be focusing on, I'll be focusing on the two parts. For this one, this is a positive one. So for this one, I'll be focusing on something like this. All right. Now another type of a parabola that you can get is it's the same one, but then it's actually negative. All right, it's a parabola. Just even though I don't draw it very nice, just know it's a parabola. So this one will be x is equals to minus x squared. All right. So even this one, the intersection is going to be at 0. Of course, I think from mathematics you'll be familiar. You could have it, maybe let's say it intersects at 4, and then you have something like this, and then this one will be like y is equals to x squared plus 4. So I'm not going to teach you maths. All right. Now, also from mathematics, you would realize, for instance, that if you another graph before I go to that we're just going to be looking at is a straight line. Straight line is just a graph like this. So this one is just y is equals to x. All right. Another one is you can have a straight line, but your straight line can actually look like that. So this one is actually y is equals to minus x, right? So all right, so these are the graphs. I'm just going to sort of try and limit my graphs to these ones, one way or the other, and then another one is just going to be a straight line graph. You could have it like that. So this is just y is equals to a constant, whatever constant that is. So I'll call the constant c. All right, and if you draw the graph below, like it's just moving here below, So it is still y is equals to, but then a negative constant. So the constant is negative, just put a positive value on the constant. That's why I put a negative. So an example would be like y is equals to -4, for instance. Then it's just going to intersect here. So for instance, this is the line that you're drawing, and then here, this is the line that you're drawing. So I mean, this could be something like y is equals to 4. So if it's +4, this value here is going to be 4, basically. And then this one is going to be -4. So it's just intersecting there at -4. So we're going to be looking at basically these types of graphs, y is equals to x and all of that. Okay. So those are the types of graphs that we'll be working with in this section. And then so I'll just try and combine everything given these types of graphs, and then I'm going to plot graphs, and then we're going to actually describe motion using these types of graphs. All right, so that should be fine. So let's see, and then now we're going to talk about things when we talk about these graphs. All right, before I introduce the graphs themselves. All right, now, let me say you have a graph. Let's just start with the parabola. So I'm just going to draw the positive side of the parabola. There it is. I have a graph like this. There's a couple of things that you need to note. I can draw a line. There's a line. And then when I draw a line that actually touches that point, just only that point. All right. If I draw a straight line that is going to just touch that point, only that point. This straight line is not very straight, but it's a straight line, right? There's a straight line. So this straight line is called a tangent, right? And this tangent, what it gives you is the slope of this tangent, all right? So you have to find the slope of this tangent. The slope is going to be equals to instantaneous velocity. Instantaneous, I forgot. So this is not correct. Instantaneous velocity. All right, so this is E, this is not C. All right, so this is instantaneous velocity. All right, so that's very important. Now it is also possible to draw a line that is going to pass 2 points. All right, it's going to pass 2 points, right? So I'm going to draw a line that passes these 2 points, passes this point. Actually, let me just first join these 2 points. It should be a straight line. Of course, guys, because I'm not drawing with a ruler, I'm not going to have a straight line as I wish to have a straight line. All right, so it's going to pass this 2 point. There's a straight line. Now this line here is known as a secant, right? I think that's how you write secant. I'm not sure. I have to look it up. Very bad with spelling. I don't know why. All right, now the slope of that secant is going to be the average velocity. All right, so if for instance we have a graph and then we are representing the average velocity, we have actually done the secant of the slope. Now the secant is not a very good approximation of what is happening here, and this is when the x-axis is the distance, and then this is the time in seconds. All right, so this is, you have an object that is moving from origin, and then it keeps increasing the distance in this fashion. Basically, that is what you are having. All right, now this xt graph, this is known as the position time graph. Okay, so it tells you, it gives you the position of the object at any given time. That's basically what it does. All right, but then the most important thing here is I wanted to just introduce these two concepts. What is a tangent? What is a secant? All right, now we can find the slope, of course. Let me just take it up as well. All right, so we can find the slope of this. So I'm just going to redraw everything. So let's just start with a situation whereby we just have a tangent. I mean, we can apply the same thing even if we have a secant. So I'm just going to discuss how we can find the slope. All right. So if I know, for instance, 2 points, if I take this point here and I take this point here, all right. So for instance, then I'll say, okay, fine. I'm going to find the value of t that corresponds to that point. So remember, this is t in seconds, and this is x with respect to t, and it's in meters, right? So I'm going to find a value here, and I'm going to find the corresponding y value here, all right, x value. And then I'm going to find another value here, and a value that corresponds, the x value that corresponds. So I'll call this x1, I'll call this x2, I'll call this t1, I'll call this t2, all right? So you can find the slope. So some people draw it like this. Then if you look at this triangle here, basically some people then say this is the triangle. So you can find the slope between any 2 points in a line, in a straight line. Now the slope is just going, I'm going to call the slope m. It's going to be given by change in y over change in t. And that is of course going to be x2, which is the second value, minus x1 divided by t2. I don't know what happened to t here. T2 minus T1. All right, guys, when you do pick up some mistakes, just move on. Sometimes we will make a spelling mistake, things like that. As long as you understand, just move on. Don't be too fast about certain things. Be too fast about physics, actually, not other things. All right. So because sometimes I do realize something that I maybe I do make a mistake and I didn't realize. You find that I wanted to write there, and because I'm just writing, I'll just say TE, but then I did say it's there, I forgot to put the H, things like that. All right, now, but I'll try and limit those types of things. But then that's not my focus. That's why my focus is more on the science itself. All right. Okay. All right. So this is fine. This is how you can find the slope. And this slope here is actually going to give you the velocity. Now it depends what did you calculate for the slope. I mean, if you calculated the slope of the secant, you would actually find, if you calculated the slope of the secant, you can actually find the average velocity. But if you calculate just the slope of the tangent, you actually find the velocity at that point. So you could calculate multiple slopes. You can calculate slope of a tangent here. You can draw multiple tangents. You can calculate the slope of a tangent here. You can calculate the slope of a tangent here, and so forth. Now, if I was teaching you guys the physics with calculus, what we would do is we'll just say this is just a graph of y is equals to x squared. So in this case, the actual graph is x of t is equals to t squared. That's how it's going to look like. So if you differentiate, for instance, dx by dt, you would actually just get 2t, which means that the slope, I mean, 2t is the same as just like y is equals to 2x, for instance, if you think of it like the graphs. And that is just a straight line that looks like this. This has a positive slope of 2. All right. So that would give you the velocity. So in actual fact, the slope is actually a derivative. But then if you take a slope at a particular point, for instance, depending if you use the first principle of differentiation, if your delta t is small as your limit approaches a certain value, basically that's what I'm saying, you actually get the actual value at that point. All right. So, but it's fine. Don't worry yourselves too much about that as well. We're gonna see how we proceed with that. All right. Okay. Now, so let me see. So what I want to do now is, that's what the slope is going to give you. It's going to give you the velocity. This is the slope of the position time graph. Okay. Now, for instance, what happens if I have a velocity time graph? So let me say I have a position time graph. Don't worry, I'll link everything afterwards. And the position time graph, and then not a position, a velocity time graph. This is the velocity, and then this is the time. The time is in seconds. This is in meters per seconds. All right. So let me just say that I have a velocity. It's a straight line already. All right. So again here, I can actually find 2 points, right? I can find this point, I can find that point, and then this is going to be T2, and then this is going to be T1, and then I can actually say this is that value. This value is going to be V1, and then you find that value is going to be V2, like that. And then what you do is you are finding the slope, so which means that the slope for this graph is going to be change in V over change in T, and then this is going to be equals to v1 v2, sorry, minus v1, and then this is going to be t2 minus t1. All right, so this is what you are going to have eventually when it comes to this. So the slope of this, remember what we said that acceleration is given by change in v over change in t. So in actual fact, the slope of the velocity time graph is going to give you the acceleration. So the slope of v versus t graph gives you the acceleration. All right, so this is what you need to know. So now I'm just going to then combine everything and then talk about what happens if how can you link, how do you link, for instance, when you are increasing distance, and then how do you then draw the velocity time graph, and how does the acceleration time graph of that instance actually looks like. And then afterwards, I am going to talk about the situation whereby I make that distance time graph a little bit more complicated. And then how does the velocity time graph look like? And also how does what you call it? How does the acceleration time graph look like? All right. So I'm going to do that now. And then after that, I'm going to talk about the areas and the integrations. All right. I'm not going to integrate per se because this is not a calculus-based course. But what I'm going to do is I'm just going to find the area using just the normal way of finding an area. All right. So how do we do this? Okay. So this is how we do this. Okay. So let me just say I have an object that moves from the origin, and then it increases the distance, and this distance is increasing following the parabola. All right, so which means that the slope is increasing steadily, right? Since this is a parabola. Okay, now this is going to be the position versus time. Time is in seconds, then position is in meters. That's what it means. All right, so this is x versus t. All right, maybe just to make it nice fine, I'll do that in the next one. All right, so I'm gonna stop putting x of t, so you'll know that x is dependent on t. All right, now the question is, what is going to be my velocity time graph? All right, if you are going to find the slope for this, it's going to be constant. So if you have a graph, if you have, for instance, distance that is increasing steadily, if it increases in a strange way, then you're going to have challenges. All right, so if it increases steadily, what is happening is that your object at zero had the speed of 0 because this is the turning point. All right, and then afterwards it was increasing in velocity. The velocity started increasing. Why is the velocity increasing? If you are to find the tangent here, the tangent here is this line with the slope. If you find the tangent here, you can see that the slope is changing, it's increasing. You can see that the slope is actually like it's more like turning up as you go, so which means that the slope is actually increasing, right? As you can see here with the green lines, I mean, you see this line here, like that. This line here is like that. So you can see that your slope is increasing. I mean, a line like this, a line like that, this one has a slope greater than this slope. If this slope here is m and this slope is m prime is going to be greater than m. So as your lines become like this, the gradient is actually increasing. As your lines become like that, your slopes becomes like that, your gradient is actually decreasing. All right, so this is what you should actually remember when you are doing this. So since here, if I draw tangents at any given point, the slopes are going to be changing, moving towards the more, to becoming more positive, basically. So if they are becoming more towards zero, then they are decreasing. If they are becoming more positive, they are actually increasing. All right, so and here, if you were to do the mathematics, I'm not going to do the mathematics, it's going to be increasing steadily. All right, so it's going to be a straight line. So this is the velocity time graph. All right, remember the velocity is going to be in meters per second, and then this is going to be in seconds. All right, so this is the velocity time graph. Now if I find the slope of this velocity time graph, right, if I was to find the slope of this velocity time graph using these two values, if you find the slope of this velocity time graph, you would actually just get a number. Why are you going to get a number? Remember, this is a straight line. Okay, so since this is a straight line, so I mean, if you like, for instance, you have a graph that is like y is equals to, actually, I don't even need to explain that, because this is a straight line. It does not matter which point you actually choose. Whatever point you choose, the slope is just going to be the same. It's going to be one number. The slope is going to be the same. Whereas when you look at this graph, because this graph is actually increasing, the slope is not going to be the same. It's going to be different depending on where you choose your points. All right. Remember, we are not using the secant, so we are not looking for the average velocity. I'm looking for the instantaneous velocity at each and every point. And that's what I'm drawing here. I'm representing the instantaneous velocity at each and every point. All right. Now, if you do that, for instance, and you find the slope of this graph, you're going to end up with the acceleration time graph. Okay. You are going to end up with the acceleration time graph. Let me say, for instance, the value of time here is 2, and maybe the value of time here is 3, and then let me say the value here is 1, and then maybe the value here is going to be 3, for instance. If you were to look for a slope for this graph, it's going to be m, it's going to be v 2, which is going to be this one, minus v1, which is going to be this one, divided by t2, which is this one, minus c1, which is this one. All right, I'm hoping in maths you did this. All right, so v2 is 3, and then v1 is 1 minus 1, and then this one t2 is 3, and then this is 2, and then you'll find that this is going to be 2 over this will be 2 over 1, so the slope is going to be 2. All right, so the slope is just going to be 2. So when you draw the acceleration time graph, oh, I said I'm not going to do this anymore. All right, yeah, I think I said I'm not going to do that anymore. I'm just going to say this is that, and this is meters per second squared, and then this is time in seconds. So what is happening is that it doesn't matter at time is equals to 0, the acceleration is 2. At time is equals to 1, the acceleration is 2. At time is equals to 3, the acceleration is 2. Right? This is time 1, 2, 3, for instance. So 1, 2, 3. Of course, this is going to be 0 here. All right, so your acceleration is constant. Why? Because the velocity is just a straight line. If the velocity was not a straight line, then the acceleration would not be this line here. It would be something else complicated. So I'm going to avoid those cases. I'm going to teach those cases when I'm teaching physics with calculus, and then we can actually go more, we can explore more options when we have calculus, because the tool that we'll be having, which is calculus, would be way better. All right. Okay, so we're gonna move on to the next section, just whereby I'm going to complicate this one a little bit and show you how you can actually link the two as well. All right. Okay, so we are going to complicate it a little bit now. So let's look at a situation whereby I have an object that's here at rest. There's my object is starting here at rest. Sorry. And then t is equals to 0 seconds. And then the velocity when it starts, since it's starting at rest, is going to be 0 meters per second. After some time, let us just say this is t is equals to 4 seconds. I have a velocity of about 7 meters per second. And then it maintains that constant velocity. So which means that v2 is still going to be 7 meters per second. And then it maintains that constant velocity, let's just say for about 6 minutes. So this is going to be 10 seconds. And then it slows down and eventually comes to a stop, and therefore is going to come to a stop. And the time, sorry, is going to take just to move from here to here is going to be 2 seconds. All right. So I'll call this point A. I'll call this okay. So I don't think you'll be able to see there. All right, let me just see if you are going to be able to see. I don't think you'll be able to see. So let's just call this point A, let's call this point B, let's call this point C, and then let's call this point D. All right, so we want to draw the position time graph of this situation. We want to draw the velocity time graph for this position, for this situation. And then we just want to draw the acceleration time graph for this situation. All right, so in both situations, you can see that the distance is increasing. It keeps on increasing from A to B to this position to this position. It is actually increasing. All right. So we can actually draw this. I'm just going to focus on drawing it. I'm not going to focus on working it out. And then I'm going to show you how you can work out, if you have a position time graph, how you can actually get the position, the actual values. So here I just want to highlight a few things. So for instance, if you want to draw the position time graph for this situation, well, since everything is going to be positive, I'm going to just have 0 here. And then this is just going to be the displacement measured in meters, the time measured in seconds. All right. So what are the times? I'm going to have 0 here, and then this is going to be 4, maybe this is going to be 10. Now this 10 plus 2 is going to be 12. I supposed to put 12 there, and then this is going to be 12. So what's going to happen between, so for instance, between actually let me go back to this color. So what's going to happen is my distance is going to increase, but then my velocity is increasing. So remember when we said that if your slope is increasing, you have something like this. If your velocity is decreasing, you're going to have something like this. If your velocity is constant, you're going to have something like this. All right. So this is for increasing. This is for decreasing. So the most important thing to note is that in both here and here, the slopes are positive. But this one is the slope is increasing, the slope is going to be decreasing here. All right. Now, all right, then this is when you have the constant velocity. So the position time graph is going to look like that. So this is how the position time graphs are going to look for each situation. So if you look at here, my velocity is starting at 0. And then at some point after 4 seconds is 7. So which means that my velocity was increasing from 0. Maybe somewhere here it's 1. Somewhere here maybe it's 2. Somewhere here maybe it's like 5. And then here is 7. So the velocity was increasing between A and B. So for increasing, I'm going to draw an increasing that, right? So it's going to be increasing. All right. Now, from here, 4 seconds to 10 seconds, the velocity is not changing, so it is constant. So I have to draw this type of a graph. So it is constant, so I just draw a straight line. This is supposed to be a straight line. I'm not very accurate because I'm just doing that. Okay. Now from here, it is moving from 7 meters per second to 0 meters. So which means that the slope is decreasing. Remember, I showed you how you can actually find the slopes. And you can also even if you should have done maths. So maths, you'll know how to find a positive increasing slope, a decreasing positive decreasing slope, and you know how to find a negative slope that is increasing and a negative slope that is decreasing. So which means here my slope is going to decrease. So I'm going to have a graph that looks like that. All right. So somewhere here 12, it has to be 0. Right. If this is 12, it has to be 0 somewhere here. All right. So let's just erase that, and then it has to be 0 here. All right. So this is how my graph is going to look like. So you join it. All right. So this is from point A to point B, from point B to point C, from point C to point D. All right. So this is how these graphs are going to look like. This is the position time graph. So how about the velocity time graph? Let's plot the velocity time graph for this situation. Right. This is the velocity here, and then this is the time here. Okay, then this is 0, it's going to start here. All right, so the velocity starts at 0, so it's going to start here. All right, and then it's going to increase up to here. So we are assuming that it's increasing steadily. Right, remember I said I'm going to limit these situations to those situations, so it's going to increase steadily for 4 seconds. All right, and then this is going to be 10 seconds, and then this is going to be 12 seconds. All right. Then afterwards, what happens? It maintains a constant velocity. Now remember what we said is that if the velocity is constant, the velocity is not changing. So it's going to look like that, meaning that the slope is 0. So because there is no change in velocity, so the slope is going to be 0. So there it is. All right. And then afterwards, it's going to move from 7. So the value here is going to be 7 meters per second. So it's going to move from 7 meters per second, which is here, to 0. So it's going back to 0. So when you still have a positive your object is still moving in that direction. All right, your object is still moving in that direction. The only difference is that when you're slowing down, the change is negative, right? The velocity is still positive. That is why the velocity is on this part of the graph. If it was negative, I was going to draw it somewhere here. But since it's positive, I'm still drawing it on the positive side of the velocity. The only problem is it's positive, but it is decreasing. So you're just moving from positive 7 to 0. So everything is still positive. Maybe somewhere here it would be 6. Somewhere here it's going to be 4, maybe somewhere here is 2, and then eventually it's 0, right? So it's still positive, and then until it gets to 0, right? So that's why it's still positive, but then the only thing is that it is decreasing. All right, so this is how the velocity time looks for this graph. All right, now how does the acceleration time graph looks like? All right, so let's see the acceleration time graph. Remember what we said the acceleration is. If I have this velocity, for instance, if I take the slope of this function here, this line, if I take the slope of this line, it's going to give me the acceleration between 0 and 4. If I take the slope of this line, it's going to give me the acceleration between 4 and 10. If I take this line, the slope of this line, it's going to give me the acceleration between 10 and 12. So let's call this point A, point B, this is C, this is from B to C, all right, and then from C to D is going to be this part, all right. So let us just find the slopes for this one. Okay, so let's just find the slope, right, from A to B, which is going to be the acceleration from A to B, because remember the slope of this graph is the acceleration. What is that? It's going to be changing v from A to B over change in time from A to B. What is the change in v from A to B? It is the velocity at B minus the velocity at A over the time at B minus the time at A. So what is that? The velocity at B is 7, and then at A it is 0, and then divided by the time at B, which is this position. This is the time position B. You just draw a straight line, and then you'll find whatever your straight line lends to, and then that is the time, so it's going to be 4 minus 0. Okay, so the acceleration between A and B is going to be 7 over 4, which is going to be 1 point something. It's just close to 2, should be like 1.7, 1.8. So 7 divided by 4 is 1.75, which is 1.8 roughly, or rounded to 1.8 meters per second squared. So this is going to be meters per second squared. All right, so you will do the same for B and C, right? You'll find the acceleration between B and C, which is going to be, the final velocity is going to be the velocity at C minus the velocity at B, which is this one, divided by the time at C. What is the time at C? This is the time at C. You draw a straight line, you go down, and then this is where your time is, time at C minus the time at B. All right, so this is going to be 7 minus 7 over 10 minus 4. So this is going to be 0 over 6, which is just the velocity between B and C is going to, the acceleration is going to be 0 meters per second squared. So you can see from this that if you have a straight line that is just flat, it's horizontal, then your whatever the slope of that line is going to be 0. Okay, so you're going to have 0. Now I am going to do the same thing, but I'm going to skip steps. I'm going to calculate the acceleration from C to D. So I'm going to calculate the slope of this line from C to D, but I'm going to skip steps because I think I've showed you most of the things that I wanted to show you. So this is going to be from C to D. The final here is going to be 0, and then the initial is going to be 7, and then this is going to be 12 minus 10. So this is going to be minus 7 over 2, which is going to be 3.5 meters per second squared. All right, so I don't want to extend this board, so it's going to be negative 3.5. It's going to be negative. I don't know, do I have space? Maybe let me just do it somewhere here. All right, so I want the acceleration from C to D. This is going to be V at D minus V at C over the time at position D, which is this time, which is 12, minus the time at position C, which is this 10 here. All right, and that is going to be 0 minus 7. This is going to be 12 minus 10. This is going to be minus 7 over 2, which is minus 3.5 meters per second. And again, you remember, because it is slowing down. So what happens when it's slowing down? The object is still moving in that direction, but the acceleration is negative. So the acceleration between C and D is in that direction. That's what it means. And then that is why the object is slowing down. So whenever you get a negative acceleration, it doesn't mean the object changed direction. I already explained this. It just means that it is slowing down. That's what it means. All right. So how do we draw all of this here? All right. So let's see the values. We have the acceleration from A to B, and we found that acceleration to be 1.8. So this is going to be the acceleration, meters per second squared. So 1.8 is going to be here. It's positive 1.8, right? And then this is going to be 4. This is going to be 10. This is going to be 12. And this is going to be the graph of time in second. All right, this is going to be 0. And then we also have the second one, which is 0 between B and C. This is going to be 0. And then the acceleration between 10 and 12 seconds, which is from C to D, is going to be minus 3.5. So let's draw minus 3.5 here. All right. So let's start with the easy one from A to B. This is from A to B. This is the line from A to B. All right. This is the line. Starts here at 0. Doesn't start here. I was just drawing this to show you. That's here. This is from A to B. All right. Now, how about the line from between 4 seconds and 10 seconds? So we say between 4 seconds, 10 and 4, between 4 and 10, it is actually 0. So we're going to draw a line here. It is 0, straight line. Right? It's constant. It doesn't change. It's 0 throughout. All right. And then what happens between 10 and 12? So between 10 and 12, it is minus 3.5. So you just, if you put a line somewhere here, it's going to be minus 3.5. All right. So that's how your acceleration time graph is going to look like. All right. So now I am going to discuss finding areas. Let me say, for instance, I'm going to use the same example, and then we're going to find the position to say, how can we find the total displacement? Like, for instance, we want to know how long did it take. Okay, we know for these 4 seconds, it reached a speed of 7, but then we want to find out how far had it traveled at that time, right? So we are going to now introduce you to using areas. Okay, all right. So okay, so I'm just going to move everything up, and then we are going to find the areas. Okay, now before I discuss finding the areas, we need to be conscious of a couple of things. So right, in order for you to find, if you have a velocity versus time graph, and you want to find uh, the displacement, right, change in x, you have to find the area, right? You have to find the area under the curve, under the graph or the curve. Let's just say, all right, let's just use the curve, right? Whatever the graph is, right? If you're at varsity, this is an equivalent of you integrating a function, right? You just integrate the velocity function, and then you get the area. So I'm not going to teach you that because this is just algebra-based physics. I don't want to talk too much about calculus. All right, so what happens then when you have that situation? When you have that situation, what you have is let's say I have this velocity time graph. So I'm going to draw the same velocity time graph. And then we said that it is going to be 7, and then it takes 4, and then it takes 10, and then it takes 12. All right, we said between 0 and 4, it increases, and then it becomes constant, and then it actually goes down like that. All right, so that's what we said. All right, I didn't draw it up to scale, something like that. Now if you look at this graph, it is for section A, number 2, and number 3, right? So if you look at section A is this one, the blue one. All right, it's a triangle. I mean, you can see here it's a triangle, right? And then if you look at the section B, is this green section here, it's a rectangle, right? It's a rectangle. So you need to be able to divide these things into triangles and rectangles. And then if you look at the other section, let's use the black color. This is the second triangle. All right. Now, how do you find the area? If you want to find the area of a triangle, this is going to be given by half base times height. So if a triangle looks like whatever, like this is the base, and then this is the height. All right. If your triangle looks like that, right, you have to divide it by that, and then this will be your height, and then this is going to be your base. All right. Okay, now another way is you can divide the base into 2, find the area of this triangle, the area of that triangle, add the 2 triangles. So you can do it like that as well if you want. All right, and then for the rectangle, if you have a rectangle, and maybe this side is the length, this side is the breadth, so the area of the rectangle will be given by length times breadth. All right, so let's just do it for this example. Let us find the area for section 1. All right, now when you find the area for section 1, you will see that you are actually going to find the position. So you are going to find how far did it travel from moving from A to B. Then how far, when you find the area for section 2, you will find the displacement from B to C. When you find the area for this section 3, you'll find the displacement from C to D. Remember what you had. You had an object that started at 0 meters per second, increased the distance, and then it reached a speed of 7 meters per second. It maintained that constant speed for about 10 seconds. So V2 is going to be 7 meters per second, and then afterwards it slowed down, and then V3 is going to be 0 meters per second, right? So remember we had this situation. So this is the velocity time graph of this situation, And then here the time is 0, here the time is 4, here the time is 10, here the time is 12. Right, so I've taught you guys about the times. So this is the time that the observer sees on the stopwatch. Okay, so this is not the time that they work out in their head. This is the time that they see on the stopwatch. All right, now if we continue with this, let us just find the area for section 1. If you find the area for section 1, it is going to be equals to half base times height. So what is the base for that? The base for that is from here to here, which is 4 minus 0. So this is going to be 4. For what? This is going to be 4 seconds multiplied by the height. What is the height? The height is from here to here, which is from this position to that position, and that position is 7, right? So this is 7 minus 0, so this is 7 meters per second. Let me write it like this, meters per second. Actually, let me go back twice. Yeah, so it's going to be meters per second. Already you can see that these seconds are going to cancel one another, and then you end up with 7 times 4 is going to be 28. 28 divided by that, and then you're going to end up with 14 meters. All right, because the times have cancelled, then you see you end up with a distance. That is why I'm saying that this distance, right, which is area 1, it is actually the area that you find here. It is the same as the position, which is the displacement from A to B. So the position from A to B is going to be 14 meters. All right, okay, now so I don't remove this, let me just erase that. Okay, let me just erase that so that I can make up some space. All right, just erase that, trying to make up some space so we can find everything here. All right, so let me see, can I still choose? Let me use a different color. All right, so now we are going to find how far did the object move from position. This is position A, this is position B, C, and D. So we want to find out how far did they move from here to here. So when you are finding areas, you are finding XAB, then you are finding delta X, BC, you are finding the displacement from delta X, CD. All right, the total displacement, which is from here to somewhere here, is just going to be delta X. All right, which is the total distance. Total displacement, of course, in this case, is going to be the total distance as well because it's traveling along the straight line. If it wasn't traveling along the straight line, it wouldn't be the case. But if it's traveling along the straight line, the total displacement generally, sometimes it depends. If it was traveling in one direction and traveling along the straight line, then the total displacement is going to be the same as the total distance. But let me say, for instance, this object went forward and then went backwards, ended up somewhere here. You can't say the total displacement is going to be equal to the total distance. I've already done an example that is similar to that, so you have to be very careful when you're analyzing this question. All right, so let's find the area for section 2. The area for section 2 will be given by half the base times the height. All right, so let's find the base for section 2. The base for section 2 is going to be this one, right? It's going to be this one. This is the, oh, I don't need the base. I'm actually wrong. Calculating it like it's a triangle. It's not a triangle. Sorry about that. It's not a triangle, so this is just going to be length times breadth. All right, so what is the length? The length is going to be this distance here. This is the length. What is the breadth? The breadth is going to be this distance here from below to the top of the rectangle, and then that is the breadth. All right, this is the breadth. So the length is going to be 10 minus 4. All right, so that is the length, which is going to be 6 seconds multiplied by this distance here, which is 10, which is 0 and 7, right? So it's 7 minus 0. So this is going to be 7. You put a positive because it's positive. The height is positive. It's going up. All right. So this is 7 meters per second. You can see also here the meters are cancelling. So and then you just have a situation whereby you have 6 times 7 is more like 12 times 3. not really 12 times 3. I don't know, I'm saying that it's more like 14 times 3 actually. All right, so which is like 30, and then 38, and then which is like 42. Okay, so this should be like 42. So this is going to be equals to 42. Okay, all right, so this is like more like 36, and then you add 6 again, it's gonna be 42 anyway. All right, so now this area 2 is the same as the displacement from B to C. So the displacement from B to C is 42 meters. Now let's find the area somewhere here for the third one, for the third section. Now the area for the third section, it is going to be, let's use a different color, let's use a blue one. So the area for the third section, which is this one, going to be, it's a triangle, not a rectangle. So with this one I can say half base times height, right? So I'm not making the mistake that I nearly made here. Okay, so this is half. Then what is the base? The base is this distance here. This is the base. I mean, the triangle is this base. Remember, it looks like that. If you draw a blue line, this is how a triangle looks like. So this is the base, and then this is the height of the triangle. Okay, so the base is, how long is the base? You just say 12. Take the final point, which is 12, minus where it stops, and then which is 10. So that is 2. Okay, so this is 2 to what? 2 seconds. Then how about the height? The height is 7 still. So you multiply it by 7 meters per second. Again, the meters per second cancel, and then this is 14. 14 divided by 2, this is going to be equals to 7 meters, right? So it actually slowed down, it actually slowed down for 7 seconds, covered a distance of 7 meters when it was slowing down. So when it was speeding up, it covered a distance of 14 meters. When it was moving at a constant velocity, it covered a displacement of 42 meters. When it was slowing down, it covered a displacement of 7 meters. Now, if you are asked to find the total displacement for the whole motion from when it started to when it ended, you can just simply say the total displacement delta x going to be delta x AB plus delta x BC plus delta x CD. All right, so what is AB? AB is 14. What is BC? BC is 7. Sorry, it's 42. I'm making a mistake. And then this one is 7. Well, if you are adding it, it wouldn't have mattered anyway, because you get the same answer. All right, so this is going to be 50, and then 56, and then plus 7, this is going to be 63 meters. All right, so that's basically how the total displacement is going to be. That's how you can find the total displacement of that. So hopefully it makes sense to everyone. And then I'm just going to maybe introduce a situation whereby how are you going to do it if you have a negative velocity. So a negative velocity would be a case like this. All right, you have an object, there's an object, there it is. It's starting at, maybe let's say already this object was already moving at 7 meters per second. Then it was moving in this direction, and then it reached this direction. Now when it reached this direction, it actually stopped, right? It stopped and then turned back, right? And then afterwards it turned back. So it turned back, of course, it's moving with this, the initial, now this speed, it becomes the initial when it's turning back, meters per second. It turns back, and let me just say stop somewhere here. So when it was moving here, the time t0 started at 0 seconds, and then afterwards it arrived at this position. Let's say t1 is 8 seconds. Then from there, this is still t 8 seconds. Let's say it just did everything, it stopped and turned in this 8 seconds, right? Of course, practically might not be really possible, but let's just assume that it can happen, right? So they stopped and turned very fast, and they did everything within this second. All right, so and then afterwards they come back, and the time here is actually so which means now they are moving in this direction. and then they end up somewhere here, and the time is, find that this is 8 seconds, so let's just say 12, and the velocity here, let's call it v2, is minus 5 5 let's just say minus 6 meters per second. All right, so how can you draw the velocity time graph for this? And then from the velocity time graph, you're going to calculate the displacement that they covered from A to B, right? This is still at position B, and then this is C. The reason why I'm drawing it like this, so that you can see that here they are going that way, and then here they are going that way. Otherwise, I could draw it in one line and say they start here, they move, they get to position B, then they come back, and then they end up at position C. So I could say this is A, this is B, and then this is C. So you see, if I drew it like this, it was going to be a little bit confusing. So that's why I drew it. I separated it, right? But then they are moving along the same line. It's not like they changed roads or something. No, they're still moving along the same road. All right, now in this case, how do we draw the velocity time graph for this thing? Okay, so I have a situation whereby already at time is equals to 0, it was already moving at 7 meters per second. So this is the velocity, and then here the time is 13 seconds, and then this is going to be 0, this is going to be 8 seconds, and then this is going to be, did I say 12? Yeah, I think it's like 12 seconds. All right, so we found out, okay, they're going to start at 7, but now they are going to end up at 0, so they are going to go down like that. It's a straight line going down like that. All right, now from 0 to 12, which is from, not from 0 to 12, from 8 seconds, because the time here is the same as 8 seconds. Remember I said that they stopped and turned within this 8 seconds, right? So from 8 seconds to 12 seconds, they actually change the direction. So which means that now their velocity is negative, and then they are going to change until they get somewhere here at -6. All right, so they change the direction, and then they move until they get to -6. All right, so this is how this graph is going to look like. All right, so let's find the position graph for this thing. Maybe let's start with the acceleration. Like, how can we calculate the acceleration? So this is from position A to position B, and then this is from position, this is to position C. So we are assuming that the observer was here when they first started seeing the car moving. They were already in the same position, because if the observer was here, then the graph would look a little bit different. All right, we'll have to do, okay, the velocity time graph would look the same, but the acceleration time graph would be something else. All right, now the position time graph, actually, sorry, is going to be something else. All right, okay, so in this case, of course, they are just slowing down, so it's fine. Time is equals to t0, is just going to be like that. Then you're going to use the information in that way it works, but then it's fine. So let's just continue with this, and then let's see how it happens. Okay, now if I want to find the acceleration, I must find the slope between A and B. So the acceleration between A and B is going to be given by the velocity at B, which is 0, minus the velocity at A, which is 7, and the time at B is 8. This is 0, so this is -7 over 8, which is going to be 0,8 something or 7 something. It's going to be close to 1. So this is 7 divided by 8. 7 divided by 8, it's 0,9. So it's very close. So it's 0,9 meters per second squared. And then what about the acceleration from B to C? Right, the acceleration from B to C, I would have to say what is the velocity at C, right? The velocity at C is -6. What is the velocity at B? Velocity at B is 0. What is the velocity? What is the time at this? C is going to be 12. what is the time at position B? It is going to be 8. Then this is minus 6 divided by this minus that. This is going to be 4. So this is more than 3 over 2, right? It's more like 1.5 minus 1.5 meters per second squared. Right, so this one is minus. I forgot to put a negative, so I put that. So if I was to draw the acceleration time graph for this graph, I would draw it like this. This is the 0, this is minus 0.9, then this is minus 1.5. All right, and then this is going to be the time in seconds. This is going to be meters per second squared. Now when you actually do that, from here this is 8 and then this is 12. So you could draw a line, remember, from 0 seconds to 8 seconds, the acceleration from 0 to 8, the acceleration is minus 0.9. So the acceleration is minus 0.9. Okay, and then from 8 seconds to 12 seconds, the acceleration is 1.5. So there is acceleration, it is minus 1.5. So that's how the acceleration time graph of this thing is gonna look like. All right, so hopefully you guys get it. Now how about the position? If I wanted to find the position for this thing, how would I find it? All right, so now I want to find the position for this thing. Okay, so if I want to find the position for this thing, how can I find it? I'm just trying to choose the color that I want to use. Now remember, if you check this thing, it has this area, right? You can just, this area here, this triangle. Just remember, you divide everything into triangles and rectangles. Then also you have another triangle, which is this one. If you extend this line, this becomes a triangle again. So you have 2 triangles here. All right, so the most important thing is to first spot a triangle and then actually do that. So this first triangle looks like this, right? It has a height from 0 to 7, so the height is going to be 7 meters per second. And then the base is going to be from 0 to 8, so this is 0, and then this is 8, so it's going to be 8 seconds. All right, because it's going to say 8 minus 0. That's the base. Then you have this one looks like that. All right, what is the height? The height is from here to here, so it's from 0 to minus 6, so it's from 0 to minus 6, so which means that the height is going to be equals to minus 6. All right, let me just try and make up some space maybe so that we can write a little bit neat. Okay, now from here, let me just erase that. All right, so the height is going to be minus 6 meters per second. All right, now what about the base? The base is from here, which is 8 to 12, so it's from 8 to 12 seconds. So when you take 12 minus 8, you're gonna end up with, the base is going to be 4 seconds. All right, so this is triangle 2, this is triangle 1. All right, so if I want to find the displacement from A to B, I'll have to find the area under 1, which is going to be half base times height. So what is that? That is half. What is the base? The base is 8 seconds multiplied by the height. What is the height? The height is 7 meters per second, right? Remember, it's 7 meters per second. Let me write it in a way that you are always going to understand, right? Meters per second, this is going to cancel, right? So you have like 7 times 8, so this is just like 14 times, this is going to be 14, and then you times it by 4 basically, which is 40, and then 4 times 4 is 16, which is going to be 56, and then the half of 56 you have to be, it has to be 28. All right, so this is going to be 28 meters. Okay, that's what you'll be left with. All right, so this is how you can find it. And then we're also going to do the area now for this one, for number 2. So the area XB for from B to C, that is going to be equals to half the base multiplied by the height. Now this is very important here. This is going to be half. What is the base? The base is going to be 4 seconds. But now what is going to be the height? The height is negative, so you're going to put -6 meters per second, right? The seconds are still going to cancel, but you have a negative number now. So now what is going to happen is, let me just make space. I think that should be fine. Just make space. So what is going to happen here is that you are going to have this half multiplied by 4 multiplied by -6 meters. All right, because the seconds have cancelled. All right, so this is 2 multiplied by -6. This is going to be -12 meters. Right, so you can see here that from B to C, it actually changed position. So which means that if you were to put this into the diagram that we drew up, if we were to put this into this diagram that we drew up, it means that the distance from A to B, the displacement from A to B, is going to be equals to 28 meters. Then the distance from B to C, which goes in that direction, that's the displacement. And that displacement delta B to C is going to be -12 meters. So you can see that it's telling you that it actually changed direction. It went on the minus direction. All right, so this is how you can actually find areas under the graphs. This is how you can actually relate everything. And sometimes they would give you a graph and then they would say write a statement on the graph. So you just follow it. I mean, if you can actually just do what I've just done here, then you can actually just come up with a statement from there. I'm not going to do that. I am going to have tutorial sessions, but those sessions will be limited because I don't have the time. I am working as well. I'm teaching, so I have to do research. So I don't have the time to have a lot of sessions with you guys. So, but I would organize additional tutorials. That's when we can actually look at your specific questions. Okay. All right. So I think this is it with this section, and then we'll see you guys in another section. Cheers.